Hello dear students, let us start module 2 of 17CS63 System Software and Compiler Design subject, that is Loaders and Linkers. The source program written in assembly language or high level language will be converted to object program which is in the machine language form for execution. This conversion, either from assembler or from compiler, contains translated instructions and data values from the source program or specifies addresses in primary memory where these items are to be loaded for execution. So, this particular process contains following three main important processes. Those are loading, linking and relocation. Here in this particular block diagram you can see assembler, linker and loader. Let me explain what are the objectives of all those modules. Firstly what we have to do is we have to write source program and give the source program as an input for the assembler. We have studied in the previous module that the assembler produces object code, in the sense object program, which has to be linked and loaded for the memory for execution. So assembler produces object code. That object code has to be given as input for the linker. Suppose we have different object programs, that is a main program is divided into subprograms and those subprograms are converted into different object programs, then they have to be linked together. Then after linking it will produce an executable code. That executable code has to be given as input for the loader, and finally it has to load the program of executable program into the memory for execution, from where program starts its actual execution. So a loader is a system program which takes the object code of the program as input and prepares it for the execution. That is, we can call it as pre-processing phase. Programmers usually define the program to be loaded at some predefined location in the memory. So, programmer can specify some address in the memory, but this loading address given by the programmer is not to be coordinated with the OS. That means the address given by the programmer need not match with the address given by the operating system. So the loader does the job of coordinating with the OS to get the initial loading address for the executable file. .exe file means executable file, and load it into the memory. The matching between the starting address given by the programmer and the address which is given by the operating system has to be coordinated. This coordination will be done by the loader. That is the main important function of the loader. Then we will study different functions, that is basic loader functions. Very important. You may get a question under this topic. What are the different basic loader functions? We have four important functions like allocation, linking, relocation and loading. Let me explain one by one. First we will go for allocation. Allocation means it is allocating the space in the memory where the object program would be loaded for execution. Space allocation will be done using this phase. It allocates the space for the program in the memory by how? By calculating the size of the program. Size of the program means length of the program. How much amount of memory is needed for that particular program. This is called as allocation. We have different types of loaders. Let us discuss later the types of loaders. Here in the case of absolute loader, what happens is allocation is done by the programmer, and hence it is the duty of the programmer to ensure that the programmers do not get to overlap. Absolute loader means the address has to be given by the programmer itself. So the programmer should ensure that programs do not get to overlap. In another method, that is relocatable loader allocation, it is done by the loader. Hence, the assembler must supply the loader the size of the program. Only the length or the size of the program has to be supplied by the programmer, and actual allocation is done by the loader itself. This is about the first phase, allocation. Next we have linking. Linking process. Linking, as the name indicates, it is linking of two or more object codes and provide the information needed to allow references between them. So it is needed when a lengthy source program is divided into submodules and those submodules are assembled separately. After assembly, they have to be linked together. For that purpose, we need linker. So it also resolves the symbolic references in terms of code as well as data between the object modules by assigning all the user subroutine and library subroutine addresses. This activity is called linking. Linking of user subroutine and library subroutine is also done by the linker module. Again, we have two types of loaders. In the absolute loader, linking is done by the programmer, and in the relocatable loader, linking is done by the loader. Hence, the loader assembler must supply to the loader the locations at which the loading is to be done. So that is about the second phase. Next, third phase is called as relocation. You have studied about relocation in the previous module, isn't it? So relocation means it modifies the object program by changing the certain instructions so that it can be loaded at different addresses from the location originally specified. If the starting address given as 0, then the object code may vary. If the starting address is 1000, then the object code may vary. So relocation in the sense, it is nothing but changing the certain instruction so that it can be loaded at a different address from the location originally specified. There are some address dependent locations in the program, such as such address constants must be adjusted according to the allocated space. Such activity done by the loader is called relocation. I think you remember about format 3 and format 4 instructions which we have studied in the previous module. Format 4 instructions, which are highly dependent upon the starting address given specified by the user. So we require one more record called as modification record to indicate relocation. So let us consider relocation and modification once again in loader also. So in absolute loader, relocation is done by the assembler as the assembler is aware of the starting address of the program. See, always remember, for absolute loader, we have to remember the starting address of the program. It has to be supplied by the programmer. And in case of relocatable loader, relocation is done by the loader, and hence the assembler must supply only the location where the relocation is to be done. So this is about the third phase, that is relocation. Next we have the last one, that is loading. It brings the object program into the memory for execution. That is the final step, bringing the object program into the memory for execution. Finally, it places all the machine instructions and data of corresponding programs and subroutines into the memory. Thus, program now becomes ready for execution. This is called as loading. Becoming ready for execution, that activity is called loading. In both the loaders, that is absolute or relocatable loader, loading is done by the loader itself, and hence assembler must supply to the loader the object program. The assembler must supply the object program for the loader, and the remaining functionalities will be taken care by the loader. So this is about 4 basic loader functions. Let me recall once again. The basic loader functions are allocating the memory, linking of user subroutine and library routines, relocation, as well as loading. These are the 4 basic loader functions. Very important, please remember. Now we have different types of loaders. They are absolute loader, bootstrap loader, relocating or relative loader, and direct linking loader. Let us examine one by one. First one is about absolute loaders. Absolute loader, as I explained you earlier, absolute loader means we have to remember the starting address. That is, it has to be supplied by the programmer. Its starting address is to be supplied by the programmer. Operation of absolute loader is very simple. The object code is loaded to the specified locations in the memory. At the end, the loader jumps to the specified address to begin execution of the loaded program. So it does not perform linking and program relocation. Only allocation is sufficient. It uses just one pass, header record, that is, the header record is checked to verify that the correct program has been presented for loading. So as an example, let us consider one program. The contents of the memory location for which there is no text record is shown as X, X, X and X. That is, contents are not important, contents are not there. For each byte of the assembled code is given by using this hexa representation in the character form. 2 points you remember. Where text records, the memory locations where text records are not there is indicated by XXXX, and each byte is represented in hexadecimal form. The main advantage of absolute loader is simplicity and efficiency, but there are disadvantages too. The need for the programmer to specify the actual address, hence difficult to use subroutine libraries. Now consider this object program. This object program is very familiar to you. It is the object program of your copy program. That is, read the contents from one device, namely 05, and copy it to F1. Okay, something like that you have studied in the previous module. So let us consider the same object program, which has got 3 types of records here: header record, then text record, finally end record. Header record contains letter H followed by the name of the program, followed by total length of the program and starting address. Text record, you can see total 5 text record over here, like this. 5 text record are there. Letter T is followed by starting address, which is followed by the length of this text record. I think you know how to compute this length. Then all the object codes in the order. Then after writing all the object codes in the text record, we have end record, letter E followed by the starting address. This is the object program that has to be loaded into the memory for execution. Now this is the snapshot of the main memory as seen by the loader. See, you can see the memory address over here starting from 0. Okay. Then according to the copy program, let us consider starting address as 1000. So from 1000 you can see the object codes. See, this is the first object code 14103348. I think it is the object code of STL return address, followed by its second object code, third object code, and so on. Then see, here also you have XXX, here also some XXX. Do you remember what is the indication of X? X means the memory location where there are no text record according to our copy program. After some instructions, after 1030, address 1030, next object code is loaded at the address 2030 only. Why? Because I think there is one memory reservation assembler, memory reservation instruction, reserve byte or reserve word, something, reserve word 1000, right? So 1000 words are reserved, so there are no object codes in the memory location from the memory location 1030 to 2030. They are indicated by XXX. Here they have put just a dot dot indicates it is XX only. So it is followed by remaining object codes. So this is the snapshot of the memory which is seen by the loader. The loader has to load this object program into the memory for execution. This is just explanation how exactly the loader will think the object codes. STL instruction which contains pair of characters 1 4. So I remember the opcode of STL instruction is 1 4. When these are read by the loader, they will occupy 2 bytes of the memory. That is 1 4. One ASCII value of 1 is 31 and ASCII value of 4 is 34. If it is read as string 1 4, then ASCII value is 31 and 34. But when 14 is represented in hexadecimal form, it requires just 1 byte. 1 is represented by 0001, 4 is represented by 0100. Okay, understood the difference? When it is represented as a string, it will occupy 2 bytes of the memory. Okay, string means ASCII value, so 2 bytes of the memory. When it is represented in hexadecimal, we require 1 byte. So the thing is, we have to convert the string into hexadecimal form. For execution, the operation code must be stored in a single byte with the hexadecimal value of 40. That is the need. Why we have to convert string into hexadecimal? Hexadecimal requires only 1 byte. Each pair of bytes must be packed together into 1 byte. Pair of bytes in the sense 14 has to be packed together into 1 byte. Each printed character represents 1 half byte, that is hexadecimal digit in the memory, and 1 byte in the object program record. Okay. Each printed character in the sense one single character means 1. Its ASCII is 31. So it is half byte. Don't consider this string value 31. When it is represented in hexa, just half byte. See here, just 0001. To represent 1, we need half byte. That is, 1 byte means 8 bits. Half byte means 4 bits. So to represent 1, we need 4 bits 0001. So when it is represented in the memory like hexadecimal, so it requires half byte and 1 byte in the object program record. There is an algorithm for an absolute loader. So let me explain this algorithm. First read the header record. Then header record contains program name and length. Remember no? Letter H followed by copy, okay, followed by length of the program. Next what we have to do? While record type is not equal to E, means till the end we have to repeat the process. If the object code in the character form like 1 4, convert it into internal representation. That is, the string 1 4 has to be converted into internal representation in the sense hexadecimal form. Then move the object code into the specified location in the memory. Move that object code into the memory. Read the next object program record. This has to be repeated, begin and end. Then finally, after converting all the object codes into their internal representation form, jump to the address specified in the end record. End record contains letter E followed by the starting address, right? Like this. E 1001000 is the starting address. So at the end, the program is to be loaded into the memory for execution. No? So jump to that particular address. This is about absolute loader. Next we have Bootstrap Loader. Simple Bootstrap Loader for SIC bar XE. Bootstrap Loader is a special type of absolute loader. It is a part of absolute loader only, but it is of special type. So I think you know about Bootstrap program. When a computer is first turned on or restarted, Bootstrap Loader is executed. The special program which is present in the ROM is getting to be executed. So with this Bootstrap Loader load the first program to be run by the computer, that is nothing but operating system. So Bootstrap Loader will load the operating system which are residing in the ROM and then starts its execution. Let us consider this Bootstrap Loader with the help of an example. This is the source code for simple Bootstrap Loader. Let us consider one example. Bootstrap Loader starting address 0. It is for SIC bar XE. So what does it do? This reads object code from the device F1, input device F1, and enters it into the memory starting at address 80. That is 80 in the hexadecimal. Okay, read the content from the device F1 and enters it into the memory, means store it into the memory starting address from the address 80 in hexadecimal. After all the code from device F1 has been seen entered into the memory, okay, after reading all the contents and storing it into the memory, the Bootstrap executes a jump to address 80 to begin execution of the program just loaded. The thing is, load the program into the memory for execution. First to read the contents from the input device, copy it to the memory and then start its execution. So here we use register X to have the next address to be loaded. Understood the program concept? Bootstrap Loader reads the contents from the object code from the device F1 and enters into the memory and jump to the starting address 80 for execution. Here, let me explain the code. Clear register A. Register A, it is general purpose register, or we can consider it as accumulator. Clear the register, that is to 0. Clear the register A to 0. Now register A contains 0. Next instruction is LDX hash 128. LDX means load register X with 128. This is decimal 128, which is equivalent to hexadecimal 80. If you convert 128 into hexadecimal, you will get 80. So here you have to supply decimal 128. Then loop jump to subroutine get C. Get C is a subroutine which is there in the next slide, which is used to load a character, read a character and convert it into hexadecimal, that is 0 to 15 or F. How to read and how to convert it into hexadecimal, that is there in the subroutine get C. After reading one character, read hexadecimal digit from the program being, because we are reading only the we are reading an object program from the device F1. So if it is there in the hexadecimal, then it is fine. If it is not there in the hexadecimal form, we have to convert. Then after getting one character, for example 1, okay, RMO register move A, S, that is contents of A must be stored in register S. Then shift L S, 4, that is we have to move first 4 bytes into higher order 4 bits of byte, that is, see, this is 1 byte means 8 bits. After reading, consider 14 STL instruction 14. After reading the first digit 1 from the device F1 and it has to move into higher order bits, that is like this. 1 means 0001. It has to be loaded into higher order bits. Then jump to subroutine get C to read the next one, that is we have to read the character 4. Okay, so after 4 has been read, then add R S, A. Okay, A contains this 4 and S contains 1. Then store character 0, X, store at the address in register X. Add R S, A will combine 1 and 4. So 4 I will write 0, 1, 0, 0. Now ticks R. Ticks R means add 1 to the contents of index register X, add 1 to the memory location, memory address being loaded. That is, we are making ready the register, index register for reading the next character. Then jump loop until end of the input is reached. Okay, got it? Read one character from the object code, object program, and store it into the memory. Next, read the second character, store it into the memory. Like that, we have to repeat till we read all the characters. Now, getC function, how it works. It is the subroutine. getC is the subroutine to read one character from the input device and convert it from ASCII code to hexadecimal digit value. The converted digit value is returned in register A. When an end of file is read, control is transferred to the starting address, that is hexadecimal 80. So function of getC is to read the character from the input device and convert it from ASCII to hexa, and when end of file is reached, control is transferred to the starting address. First, test the device. TD for test device. Test whether the input device is ready. Jump on equal getC. Loop until ready. Then RD input. Read the device from the input device. Read the content from the input device. Compare #4. If the character is hexadecimal 4, that is end of file. It is the ASCII code of end of file character. So compare with the end of file. Jump on equal 80. If it is end of file, go to the address 80. Next what we have to do? If not, compare with 48. If it is not end of file, then compare with the 48. Why it is 48? 48 is the ASCII value of character 0. When it is converted into hexadecimal, you will get 30. So we have to convert ASCII to hexa. So 0 to F we have to consider. So first check whether it is 0. So compare with 48. Jump less than getC. If it is less than 48 means we have to skip the characters less than 0. Negative values has to be skipped. So jump less than to get character. Otherwise subtract 48. Subtract 0 from the ASCII code. Suppose it is 0, 48 minus 48 you will get 0, hexadecimal 0 only. So suppose it is 49, then 49 minus 48 you will get 1, hexadecimal 1. So ASCII value of 2 is 50. 50 minus 48, see subtract 48 no. So 50 minus like this. ASCII value of 2 is 50. 50 minus 48 which is equal to 2. So decimal value 2 is equal to hexadecimal value 2. So we have to repeat till we reach 9. How will you represent 10? So compare with the 10. 10 is represented by capital letter A. So if it is less, then return. Otherwise we have to subtract 7. I think you remember the ASCII value of capital letter A is 65. ASCII value of 9 is 48 plus 9 you will get. So next 7 you have to subtract. So to get from A to F you have to subtract 7 from the ASCII value of corresponding letters. Then return to subroutine. This is the code for the input device. Then end loop. This is about Bootstrap Loader. Very important. Either absolute loader algorithm or Bootstrap algorithm will be asked in the examination. So this is just explanation which I have explained earlier. Once again go through the points. Bootstrap itself begins at address 0 in the memory. It loads the OS or some other program starting at address 80. Bootstrap Loader itself begins at address 0 and a particular program begins at address 80. Later, each byte of the object code to be loaded is represented on device F1. F1 is our input device as 2 hex digits. ASCII code for the character 0, that is hexa 30, is converted to numeric value 0. 1 is converted to numeric value 1 like that. Object code from device F1 is always loaded into consecutive bytes of the memory starting at address 80. How is the loader itself is loaded into the memory? Do you aware about it? An absolute loader program is permanently resident in a read-only memory, as I told you earlier. It is permanently stored in ROM. Whenever a hardware signal occurs, that is whenever you switch on computer, the system starts switch on the computer, then the first program which has to be executed is operating system. Bootstrap loader will load the operating system into the memory for execution. So the program is executed directly in the ROM. The program is copied from the ROM to the main memory and executed there. This is how Bootstrap loader will execute operating system. But this absolute loader has got several disadvantages. What are those? One is knowing of actual address. The actual address at which it will be loaded into the memory has to be known for the programmer, but sometimes it is difficult to know which part of the memory is free and which part of the memory is already allocated. If the programmer specified address is not free in the main memory, then the programmer has to change the address. So that is one of the disadvantages. Another one is it cannot run several independent programs together, sharing memory between them. That is another thing. We cannot run several independent programs together with the help of absolute loader. And last one, it is difficult to use subroutine libraries efficiently. With respect to absolute loader or simple bootstrap loader, it is difficult to use subroutine libraries. To overcome these disadvantages, we have next method called as relocating loader or relative loaders. Let me explain those relative loaders in the next video. Thank you.